Hello. So today we'll be solving linear ODEs with constant coefficients. There are three problems that we want to solve today. For part A, we want to solve x dot plus kx is equal to 1. In the second problem, part B, we're just changing the right-hand side. Instead of 1, we have e to the minus 5t. And finally, in part C, we have a superposition of those two right-hand sides. So we have x dot plus kx is equal to 4 plus 7e to the minus 5t. All right. So the first step in solving these problems is finding the homogeneous solution. We do this by setting the right-hand side equal to 0. Actually, note that all these three problems have the same exact left-hand side. So the homogeneous solution will be common to all of them. So we just have to do this problem once, and we'll have the homogeneous solution for all three parts. So let's do that. X dot plus kx is equal to 0. We're going to use the characteristic polynomial. The characteristic polynomial of this equation is denoted by p of s, and is equal to s plus k. We find the solution to the homogeneous problem by setting p of s equal to 0. That would tell us that s is equal to negative k. Therefore, our homogeneous solution, which will denote x of h, is equal to e to the minus kt multiplied by any constant. All right. For part A, now we need to find a particular solution that satisfies the differential equation x dot plus kx is equal to 1. Now, this is an equation that we can actually solve by inspection. If we assume that x is a constant, then x dot is 0. We just ignore it, and we're solving kx is equal to 1 if x equals a constant. And we can get that x is equal to 1 over k. And that's a particular solution. We'll denote this particular solution by the subscript a. So x sub a is equal to the particular solution to part A. Now, the general solution to part A would be given by the particular solution that we just found plus the homogeneous solution that we found in the previous step. So x is equal to 1 over k plus c e to the minus kt. And that's our final solution for part A. We use the method of inspection, and that's not the most systematic way of doing it. There are other methods to solve this equation, and we'll get back to that. But for now, I just wanted to show you that there are ways to solve ODEs that are very simple just by looking at them. But don't worry, we'll look back at systematic methods. Now for part B, we're looking at x dot plus kx is equal to e to the minus 5t. And now we'll use the systematic method. We're going to use the exponential response formula, or ERF. We can only use the ERF because the right-hand side, or the forcing of this equation, is exponential. In order to calculate the solution, the particular solution to this problem, we take the right-hand side, which is e to the minus 5t, and divide by the characteristic polynomial p evaluated at minus 5, which is the coefficient here in the exponent. So we have xb is equal to e to the minus 5t, and we refer back to the characteristic polynomial that we had before. So we plug in minus 5 for s. So we get minus 5 plus k. And this is a particular solution for part B. We can again write the general solution to part B by adding the particular solution and the homogeneous solution that we found before. So for this part, we have x is equal to e to the minus 5t. I'll just rewrite the denominator to look nicer. And we add the homogeneous solution. And this is the general solution for part B. Note an important thing here. What happens if k is equal to 5? Then this denominator goes to 0, and this solution is undefined. We'll need to look at another method to solve this. But just one last thing that I want to point out is that the ERF could also have been used here in part 1. If we think of 1 as e to the 0t. That's true, that's an exponential, and if we use the exponential response formula, we would have gotten the same answer. You should try that. We'll go back to the case now where k is equal to 5 in the next video. All right, so we just found a solution for part B, but we notice that there's a problem when k is equal to 5. So this solution actually is only valid if k does not equal to 5. Let's look at the other case. If k is equal to 5, we're actually solving the differential equation x dot plus 5x is equal to the e to the minus 5t. Now, since we saw that the exponential response formula as we know it didn't work, we can use the method of variation of parameters. So for variation of parameters, we need a homogeneous solution, which we found before. We found that it was e to the c times e to the minus 5t, because in this case, k is equal to 5. But for the method of variation of parameters, we only need one homogeneous solution. So we can take c to be 1, and that will make the algebra easier. So now, x will be equal to u, our introduced parameter, which is a function of time, times e to the minus 5t. We plug this into our ordinary differential equation, and we get d dt of u e to the minus 5t plus 5 times u e to the minus 5t. And all of that has to be equal to e to the minus 5t, which is our right-hand side. Now, we use the product rule to simplify this term, which gives us du dt is equal to, du dt times e to the minus 5t. Then we get a minus 5u e to the minus 5t plus 5u e to the minus 5t. And all of this is equal to e to the minus 5t. As it always happens in the method of variation of parameters, these two terms cancel out, because the product rule makes sure that the homogeneous part of the equation is guaranteed. So this cancellation is normal of the method of variation of parameters. Now, if we multiply both sides by e to the 5t, we would get that du dt is equal to 1. And this is a quite easy differential equation. We just get that u is equal to t plus a constant c. Now we plug that back into our expression for x. So x is equal to t plus c times e to the minus 5t. Let's just rewrite this here. X is equal to t plus c e to the minus 5t. And this is true when k is equal to 5. Note that this part contains a particular solution, t e to the minus 5t, as well as the homogeneous solution, c e to the minus 5t. So by using the method of variation of parameters, we got both solutions at the same time. That's a nice feat of the method of variation of parameters. Now, in part C, we're asked to solve x dot plus kx is equal to 4 plus 7 e to the minus 5t. We need to note that that the right-hand side is a superposition of the first problems that we solved. So the 4 is the same thing as 4 times 1. And the second term is 7 times e to the minus 5t. And these were the right-hand sides on parts A and B. So we're solving this problem. Because this equation is linear, we can superpose the solutions that we found in part A and B and get the particular solution for part C. So the particular solution for part C is recovered by multiplying the solution for part A times 4 and the solution for part B times 7. Note that once again, this is the particular solution. If I want the full solution, I would get the general solution by adding the particular solution plus the homogeneous solution that we found before. So we have x is equal to 4xa plus 7xb plus a constant times e to the minus kt. And this is the most general solution that we have for part C. And with this, we're done with this problem.